how to make a star do what it does. And I'm gonna be trying to review some of the recent kind of like theory behind these kind of things. And the short answer is that it's complicated, but we'll try to unravel some aspects of it. And just a comment, I may use the whiteboard at some here and there. I was told this one is better, so maybe while I do it, you can maybe move a bit, or I don't know. But yeah, it could be a bit challenging. See, I'm not going to use it too much, maybe like a few minutes here and there, but it may happen because it's the theoretical school, because the T is for theoretical. So I kind of feel like I should be using markers and write stuff on the board. Otherwise, I don't feel whole. Okay. Okay, good. There's some. Okay, finally my jokes are working. Okay, I'm glad to learn that. Okay, and yeah, so cut me off at like 45 minutes from now. So hopefully it'll be Okay, so yeah, so I think the question is, okay, we have tidal destruction events. They have been predicted even before they were observed. And maybe we can just go onto like a voyage into our galactic center. Yeah, there's going to be some outline. It has a lot of like scary words over there, like two-body relaxation and some kind of terms that we're going to be using. Actually, I failed to make all the slides on time, so I may skip some later sections, but we'll see. Yeah, so anyway, I think, if you want to think of like supermassive black holes and galactic centers, maybe it's good to start going a bit way back to the 1700s, I guess, where, I think, the center, like central of stuff was a very philosophical niche back then. And Kant, who correctly predicted the nebular hypothesis on how planets form, was completely wrong about what happens in the galactic center. He thought that, that Sirius is a giant star and the sun revolves around it. So we know it's not really the case. But I mean, these ideas on where's the center of the galaxy or the universe or whatever, it has been like around for hundreds of years. And so it's been on our minds for a while. And essentially, after Flash moving forward, also in the early days of radio astronomy, there was some spurious radio sources from the center of the galaxy. I think now it's called Sagittarius A, based on some constellation that was back then. I think it's still there. And later measurements also figure out that it's actually located around 8.3 kiloparsecs from the sun. And moreover, once we got better with technology and stuff, we were able to actually observe some of this very dense, like very concentrated environment, and we could have looked for decades basically onto this like central arc second. And the definition of arc second is basically, if the distance is like 8.3 kiloparsec, then 1 arc second is going to be the same number but in AU, because that's the definition of a parsec. If you think about that, so that's convenient. And so once there's been some close monitoring of the galactic center for several of years, and we see these motions of the stars in the sky basically. And they look very weird, and it seems to be something in the center that may be kind of pulling them together. And basically once you kind of like do these points on the map, you can trace the orbits of some massive stars that are in this environment. And and of course that gave people Nobel Prizes and etc. And it was like a very fun experiment we've done. It was like, and also from the orbits of these stars, you can also measure the mass of the central object, which is a few billion solar masses. I should have said it here, but it is. And and this environment really has like hundreds of young stars, they're massive, therefore they're young, so it's a bit weird. And it's a bit unclear how they form or whatever. But moving back to tidal disruptions, I think you've already seen this cartoon. It's actually of my former office mate that I forgot to credit, but I can tell you his name later. In any case, so if we have supermassive black hole, as you've seen earlier this morning, and there are some stars nearby. They actually look like they're on some elongated orbits, like this S2 thing. It's very eccentric. It's like, I think it's eccentricity of 0.9 maybe. And yes, so basically we know that, I think as Katie has shown you, that whenever the star comes too close, eventually the gravitational pull of the supermassive tidal force from the supermassive black hole will overcome the gravitational pull of the star and it will be disrupted. So that's our tidal radius. And some, at least theoretical estimates, kind of estimate the number of these things roughly 10 to the minus 4, minus 5 per year, which is, it doesn't sound a lot, but I think in astronomical numbers, it's quite frequent. It's like our galaxy should have had like 10 to the 5 TDEs already, which is, sounds a lot. Yeah, and just to like see like what's the scale of this phenomena, you know, we kind of have to think of like what are the typical length scales we have in the system, and what's the dynamical range that we have in studying these problems, and why it is hard because of the dynamical range. Yeah, so if you just look on length scales, for example, then we can also think, you know, if we have some black hole of some mass m, we can calculate the gravitational radius of it. Basically, it's like half of the Schwarzschild radius. Basically, that's where the velocity is roughly the speed of light. And at least for our galactic center of the mass we have, it's a few percent of NAU, which is pretty close. And if we take a solar mass star, our tidal radius is going to be roughly NAU, pretty much. It's still much larger than the gravitational radius, and for this mass at least. And this is important because if our star moves on a radial orbit, then it first encounters the tidal radius, but you can still do Newtonian physics to approximate that motion. You don't need to invoke GR. Maybe Spencer is not happy with that. If you want to invoke GR, you want to go to larger masses of the supermassive black hole such that both radial will be comparable. So I think around 10 to the 8th solar masses, relativistic effects will matter eventually once you simulate these disruptions. Are we going to do that tomorrow in the tutorial maybe? No? Okay, we'll see. No spoilers, I don't know. Yeah, so anyway, but at least for lower mass supermassive black holes, we don't really need to think about relativity too much. We'll see later that we still need to think about that sometimes with respect to other stuff. And yeah, and I think at least the outermost scale that we can think of is actually something that's called the sphere of influence. And the idea is that, you know, you have your supermassive black hole, and you have some cluster of stars nearby, and as you go out, this number of stars is increasing, and the mass of the star is also increasing until eventually, far enough, the mass of the stellar cluster will be comparable to the mass of the supermassive black hole. And if we do some rough estimate, at least for a galaxy, it's around a parsec. So usually people say, it's around a parsec, or some people are going to say the central parsec, some people will say the sphere of influence, and etc. But they kind of mean the same thing. That usually, you know, if you wanna model like how a star moves around a supermassive black hole, you shouldn't care about the neighboring stars too much over short periods of time. It will be on a Keplerian orbit. Only over long time scales, you may need to do some corrections. Okay, so now we have these scales. Basically, we move from a fraction of NAU, or at least AU for tidal radius, to a parsec, which is roughly 5 or 6 orders of magnitude. And then the question is, okay, but how do we get from being close to the sphere of influence or somewhere else? How do we become so eccentric and so radial that we eventually will be disrupting? This must be a very peculiar orbit. And maybe we can do a survey. So yeah, where do you think that the stars are coming from that disrupt? Is it A, from the sphere of influence? Is it from the central region of the central arcsecond? Is it something close enough to the tidal radius that maybe you scatter a bit? Or maybe it's a conspiracy theory and the Earth is flat and there's no such thing. So yeah, who thinks it's A? Don't be shy. Who think it's B, from the central arcsecond? Okay. Okay, who thinks it's C close to the Tidal radius? Okay, so you must be all thinking it's a conspiracy theory, right? Yeah, so it seems like we don't have a strong scientific favorite. Yeah, maybe we can try it again, no? So we haven't decided yet. Okay, maybe we can try again and see what happens. Who thinks it's A? Okay, 3 people. Who thinks it's B? Okay, so it's 5, 6. Okay, and C? Okay, just for the fun, let's check who thinks it's D. Okay, yeah, so I think, good, I misled you in a clever way. So actually, when you look on that, it's a bit surprising and counterintuitive that actually most of the TDs are actually coming from really close to the sphere of influence, from not a galaxy far away, but enough far away. And this is a bit surprising, and I think we'll try to, hopefully we'll try to understand why this is so. And yeah, and you know, it's a bit not intuitive, and it's a bit tricky. Yeah, so we'll try to unravel roughly why is it happening. But yes.
Just related to the distribution of eccentricities of the sphere of influence?
Not necessarily. It relates to how it's easy to stir a star. It depends where it is.
So I guess I'm asking is that is there some tendency for stars to have a broad distribution of eccentricity? And that then there'd be a small population of stars that get very close.
Yeah, there is kind of, yes. And I think the trick is that where do you want to be, that you want to, you know, move the stars fast enough to be very eccentric. And yeah, so you want to have something exterior to the stellar orbit to change its orbit. And okay, you know, I think the short answer is that if you're too close, you don't have enough other stuff to push you around. But if you're too far, it's actually easier to push around. Also, the number density of stars outside is larger. So even though maybe it's less probability per star, you have more number of stars that do it. And also, if you're too close, usually there's some other effects that that prevent you from doing that. A bit, yeah. I know it's surprising, but yeah. Anyway, so and the trick is that, yeah. Okay, I had some scary equations. Never mind. We're gonna get to it soon. And the thing is that it's eventually about diffusion, because the idea is that we have the central black hole, which is fine. We have a star. It moves on a Keplerian orbit. And then, you know, over some time, maybe you have some close encounters with some other stars, and it moves it a bit in some parameter space. So I think here I've chosen to plot basically either separation, like the energy or the separation, or maybe the pericenter, and see it evolve. Here it's like a similar plot where you have some diffusive models for galactic nuclei that people have been working on. And I think the idea, at least the gist of I think that's like the important plot of the talk. That's like the gist. So if you're starting like very far, you're able to diffuse quite rapidly, and you're mostly diffusing in angular momentum, while your energy doesn't change that much. You can just kind of like plunge into the disruption radius. But if you're too close, you could have some other effects, such as geometristic precession or gravitational wave dissipation, and some other things that come from GR that prevent you from going too close. And the reason is that, yeah, we're going to see what's the reason. Okay, so I think that's something to need to think about, that to bear in mind, that we're going to try to explain these trends. And yeah, and I think one way of doing that is like a kind of like a simple, I mean, relatively simple kinetic theory, in the sense that, okay, we have like a million of stars in the galactic center. Let's not think about each individual star at itself. Let's think about maybe some probability of phase space or whatever. So this F, we just call the distribution function. Basically, it means, or at least you can also write this down. It doesn't have to be like position and velocity. It could be energy or angular momentum if it's a spherical potential. It could be some other integral that depends of the axial symmetry of your potential, and etc. And yeah, and basically the idea is that, oh, I forgot. Yeah, so if you have some volume element in this phase space, And yeah, and the probability to find a star over there, it's basically integral over this distribution function over some volume. And we can also then marginalize over the velocity, basically iterate out to get the typical, yeah, kind of like a number density of stars at some location. And once we have a number density, we can also think of a potential and have like a Poisson equation, etc. And if we don't have any collisions or any external stuff, usually our distribution function, you can think of it as a flow in some sense. Maybe the hydro folks here can relate a bit, thinking of as some kind of like incompressible flow that basically you can't really squeeze that thing too much. You have to conserve the probability density in some sense. So yeah, and that thing is usually, so I think this full derivative is sometimes called the convective derivative, to maintain the analogy of fluid dynamics that indeed the change, basically if you don't have any collisions or some external, you don't really change your distribution function that much. I think that sometimes it's called, if your interaction term is 0, sometimes it's called the collisionless Boltzmann equation that basically governs how distribution function of some dynamical system evolves. And the thing is that it's a bit tricky. There's a lot of like small pieces which is hard to explain, but the idea is that it is usually done for systems which are out of equilibrium, because our interactions are long range, and it's not really, it's evolving. So that these set of equations kind of like govern you how things evolve towards equilibrium, hopefully. I hope it's clear enough. Okay, I think we're kind of on time. Yeah, do I want to do that now? I think I have to, right? What have I done to myself? Yeah, okay. Okay, so maybe we'll, let's see. Okay, so yeah, and I think one way to want to start here and maybe get some typical equation of, how they deal with these things. It's something that's called the Fokker-Planck equation, which is, it's a bit tricky to explain, but I can try. So do I want to derive this or not really? But maybe I should try and do it and see where do we go. So yeah, we want to start from some, okay, it is the following. I just told you that maybe the equation is collisionless, but but eventually, if you're gonna have some cluster of stars and they're gonna interact, you will have some encounters and things will change. So we do want to kind of account for that. So I think the idea behind this thing is that let's pretend we have some volume element here, delta W. Well, I think W is going to be basically the position and the velocity in some phase space. And the idea, it's a bit like a grid code, basically, in some sense. I think maybe I'm wrong, but maybe you have some like neighboring volumes, I don't know, or whatever. And things, a star could be in this place in action space or phase space. It can be scattered out. Maybe it will get a kick and go here, or maybe here. So the volume does change. Also, maybe some neighboring star could be scattered in also. And it has like a different probability here because the volume here is different. So you kind of have these kind of like exchange interactions in some sense. And yeah, you can kind of like formulate the equations that govern that. And yeah, and the idea, it's kind of a bit like I want to say a Markov process a bit. Have people heard of these things? Eventually, basically, you're moving in and out. You want to kind of like relate the distribution you have now to what you had in the past after some step. And yeah, so there's like a way to do it properly and do some approximations. And it looks like a diffusion equation. Yes?
Yeah, so maybe, I don't know, what I would say is that as you go from the Boltzmann equation and you're looking at the effects of collisions, the point being is that because of the long-range nature of the gravitational potential, you have many small angle collisions and only very few large angle collisions. Right. And if you have lots of small angle collisions, then the then you can think of it as being a diffusion, a very small, you don't go from one part in space and jump to some other part far away. And so the collisionless Boltzmann equation, the collision Boltzmann equation, the Fokker-Planck equation is basically treating that collision term as a diffusion, because it's always small, and it's always distant encounters that dominate over the large angle encounters. If you have a collision that basically changes its direction by a large amount, then you're jumping from one place in space to another. But if you're just doing it gradually from one place to another, then it's a diffusion.
Yeah, that's right. And I think we're a bit ahead of ourselves, but eventually we'll calculate something that's called the relaxation timescale. And in that timescale, you're going to have this Coulomb logarithm that people like, and that really accounts for these things, that there's some cutoff. But I think we should get to that first. Yeah, and I think the idea is the following. Let me see if I can do some heuristics of that. Hopefully I can. It's a bit tricky. Do you want to see the derivation of the Fokker-Planck, or should we just believe me that it's okay and we can move on? Because it may take like 5-10 minutes of algebra. Yes, no? It's a school we should learn, right? Yeah, I'm just gonna maybe outline what do we do, and we'll see. So I think the idea is that what we're doing, if we're on this red volume and we want to jump, so we need to like think maybe of the probability of kind of like transition or scattering out from the volume is, yeah, something like we need to weigh by our distribution function, times basically some probability that we don't know yet, delta omega, and yes, d of delta omega with some volume. And we need to kind of like integrate over all the other volumes we can jump to. So we're gonna need to, delta omega, and we need to kind of like integrate over all the possible volume elements. That's for a term that basically you scatter out. And similarly, if you want to scatter in, so if you want to, there's a minus sign because we're moving out. So if you're scattering in, it's like almost the same thing, only that d delta omega, but only now you're starting from some probability at omega minus delta omega that you jump towards our volume times distribution function at actually omega minus delta omega. So you want to jump inward. And you combine these two together, and that will be your collision term in some sense. And yeah, so basically if we have these two, it should be something like that, but it's a bit annoying because we have f here as we need to derive it, and we have f here, which is inside of an integral, which is annoying. These kind of equations are called integral differential equations, and they're almost impossible to solve because it's really hard, usually. So yeah, or unless you know how to do it. But yeah, I think you have like they kind of like appear in like many places where you kind of have like even like in Dutch graph, it's like similar equations also appear there. And the trick, the trick, as in any case, to get the Fokker-Planck, maybe I can do it here. So basically the essence of the Planck approximation is essentially we're going to take this thing and we're going to expand it, obviously in Taylor expansion because it's a small volume element, to second order because we need the diffusion term to be there. And yeah, and the idea is that you're going to take basically p times omega minus. I'm going to do it in 1D because it's easier. I don't want to, keep track of all the sums. D omega. Again, this means that I'm here at some omega minus d omega, and I'm jumping here. That's the probability of jumping. F times omega minus delta omega. So it is roughly, okay, I'm going to just write p times f at omega. I think it's easier. It's like the basically like being here, minus essentially delta omega times some first derivative of basically this thing, evaluated at omega, and plus the second term. Anyway, it's like a sloppy way to do it, but any case, you plug this in back, and then you play with the integrals and the derivatives. If you believe Leibniz rule, you can kind of like do this and switch and etc. So you can kind of like massage this a bit. Yeah, until eventually you can arrive to what's basically written here. In like this is ND, but essentially you're going to have that the derivative of our diffusion function essentially it's going to have a term that has like first derivative from the first expansion that usually correspond to the drift that we have in the system. And yes, and the other term, which is second derivative, sometimes it is the diffusion of what we have. Yeah. So if you really don't have the first term, essentially it is just a diffusion equation in some sense. And these are basically they're given by some integrals over our transitional probability, which is currently a general thing. They are the different coefficients, and the thing is that if we know that our distribution function is known, or we know how the scatterings work out, we can kind of like estimate that and calculate them, and that's fine. So it is possible. But the thing is that they're like really independent in some sense on the distribution function. They're really depending on the structure that we have, and that allows us, because yeah, we kind of like truncated that. Yeah, I forgot. There's some other term here that goes obviously as a cubic power, but the thing is that instead of solving integral differential equation, we're solving a PDE, a partial differential equation. I know it's usually hard, but it's actually easier than solving these things. So yeah, so that's what we'll be doing soon, hopefully. And yeah, and I think the idea is that also usually, yeah, so if you know the population of the field stars, we can calculate these coefficients, and we also have something that's called the fluctuation dissipation theorem. Has anybody heard of that in the context of statistical mechanics? Yeah, it's a bit, it connects, and whenever you have like a stochastic process or whatever, you're going to have some drift and diffusion, and they will be related to each other. So I think if you think of like a Brownian motion, if you have some dust particle moving in gas, you know, usually if you move back and forth, if you have some mobility, it generates heat, and it connects to the diffusion that we have. And I think the connection between the mobility and the drag sometimes is called the Einstein relations. Maybe you've heard of that. I think that's what gave Einstein his first Nobel Prize on Brownian motion. At least that was his first paper in 1905 in his magic year. That was on Brownian motion, kind of like doing these relations. Yeah, but now we kind of know that's actually like a general term that connects drift and diffusion. And yes, so I think that's what I had to say about this general formalism. And yeah, okay, we're getting close to actually doing some stuff. Okay, so what we'll do is we'll do something nice. So we still need to introduce this loss-con thing. Yeah, we need to do. Yeah, basically it is that. Why do I tell you that? Because you know this thing governs how does f maybe E and J evolves, and it's really like you have like two dimensions here, but normally we'll see that actually the change in the energy is actually much slower than the change in angular momentum in this case, even though it's the same equation, which is a bit weird. So we're going to try and solve kind of like a simplified version of it, that after do some further massages to this equation, they're usually just a diffusion equation. It's going to be a diffusion in J, in angular momentum. And the thing is that you start from some distribution function and you evolve it until eventually you want to count how many, you know, if you're going to have some, let's pretend that this is J and this is Fj. You know, if it's something like that, then it's okay. Let's say this is like J tidal or whatever, or whenever you're like have an angular momentum which is low enough such that you will be disrupted for this matter. I think it's called the loss cone, and the idea is that your angular momentum is so low that the corresponding pericenter is actually the tidal radius. So, and that's usually much smaller than a normal circular angular momentum that's associated with a star of the same energy. And yes, so we want to like do some equation and maybe evolve it a bit. Maybe after some time it will look like that. Just going to say, okay, this fraction, it needs to, this fraction of phase space of the star that reach this threshold, they will be disrupted onto the black hole. So I think that's like the rough idea. And I think in the tutorial, it's number 1. You can probably find it. And the idea is that we're going to solve like kind of like a simplified diffusion equation without any drift. You can arrive at it after doing some further assumptions that are kind of described here in this long paper. And for the initial conditions, we'll pretend that there is some anisotropy in the velocities. So it should mimic something like, you have like an infalling cluster or something that has some bursts of star formation. And usually it's not a vanilla process, it's kind of violent. So you may get some anisotropies in the velocity distribution. And this beta parameter should measure how anisotropic is that. And so I think in this example, if you just run it, you can just click run all or whatever. Let's just do it quickly. That should be like for isotropic distribution. You're going to get something, and you're thinking to try different parameters, maybe try to break the equation and see what you can get, and then and then at the end you can like estimate, okay, is this rate make sense to the observed TDE rate or stuff like that.